Logarithms often appear complex, but they are surprisingly straightforward. Imagine trying to find how many times you need to multiply a number by itself to get another number. That's precisely what logarithms help us do. Suppose we want to know how many times we need to multiply 2 by itself to get 8. We know that 2 times 2 times 2 equals 8. This means we multiply 2 by itself 3 times. In this scenario, the logarithm, denoted as log base 2 of 8, equals 3. Logarithms provide a concise and elegant way to express exponential relationships. Instead of dealing with cumbersome multiplications, logarithms offer a more manageable approach to handling exponents. In essence, logarithms are mathematical shortcuts that unveil the hidden patterns in exponential relationships. Whether we're dealing with sound intensity, earthquake magnitudes, or radioactive decay, logarithms equip us with the necessary tools to understand and manipulate these phenomena with greater ease. Logarithms demystify the world of exponents and provide a powerful tool for solving intricate problems. To navigate the world of logarithms effectively, we need to familiarize ourselves with their specific notation and terminology. The notation log base b of a equals c represents the fundamental logarithmic equation. In this equation, b represents the base of the logarithm, a denotes the argument or the number we're trying to obtain, and c signifies the logarithm itself. For instance, in the equation log base 2 of 8 equals 3, 2 is the base, 8 is the argument, and 3 is the logarithm. Common bases include 10 and the mathematical constant e, approximately 2.71828. When the base is 10, we refer to it as the common logarithm, often denoted simply as log. When the base is e, we call it the natural logarithm, represented by ln. Mastering this notation and terminology paves the way for a deeper comprehension of logarithmic properties and applications. Let's solidify our understanding of logarithms by exploring some illustrative examples. Consider the equation log base 5 of 625 equals what? This equation asks us to determine the exponent to which we need to raise 5 to obtain 625. We know that 5 times 5 times 5 times 5 equals 625. Therefore, log base 5 of 625 equals 4. Let's delve into another example. The equation log base 2 of 64 equals what? Challenges us to find the exponent required to raise 2 to get 64. We know that 2 times 2 times 2 times 2 times 2 times 2 times 2 equals 64. Consequently, log base 2 of 64 equals 6. Section 4. The intimate dance of exponents and logarithms. Exponents and logarithms share an intimate and inseparable bond in the realm of mathematics. While exponents involve repeated multiplication, logarithms provide the key to unraveling the mystery of these repetitions. The equation 2 to the power of 3 equals 8 exemplifies the connection between exponents and logarithms. Logarithms help us answer the inverse question, what exponent is needed to raise 2 to the power of 8? The logarithmic equivalent of this question is log base 2 of 8 equals 3. Understanding this intimate dance between exponents and logarithms is crucial for comprehending various mathematical concepts, particularly those involving exponential growth and decay. From calculating compound interest to modeling radioactive decay, this intertwined relationship plays a fundamental role in numerous scientific and engineering applications. Section 5. Unveiling the power of common logarithms. Among the diverse family of logarithms, common logarithms hold a special place due to their widespread use in various fields. These logarithms, denoted by log on calculators, employ the base 10, making them particularly convenient for calculations involving powers of 10. For instance, in acoustics, the decibel scale, used to measure sound intensity, utilizes common logarithms. A 10 decibel increase represents a tenfold increase in sound intensity. Another notable application of common logarithms lies in the Richter scale, a logarithmic scale used to quantify the magnitude of earthquakes. Each whole number increase on the Richter scale corresponds to a tenfold increase in the amplitude of seismic waves. Section 6. Delving into the realm of natural logarithms. Venturing further into the fascinating world of logarithms, we encounter natural logarithms, denoted by len on calculators. These logarithms utilize the mathematical constant e, approximately equal to 2.71828, as their base. Natural logarithms find widespread applications in modeling exponential growth and decay processes ubiquitous in nature. For instance, radioactive decay, a fundamental concept in nuclear physics, follows an exponential decay pattern elegantly described using natural logarithms. By understanding the half-life of a radioactive isotope, we can predict its decay rate and the amount remaining after a specific time using natural logarithms. Population growth models also benefit from the elegance of natural logarithms. The exponential growth of populations under ideal conditions can be accurately modeled using equations involving natural logarithms. Section 7. Embracing the enigma of negative logarithms. While the concept of negative logarithms might appear counterintuitive at first glance, it follows the same fundamental principles as their positive counterparts. Instead of asking how many times we need to multiply the base, negative logarithms inquire about the number of divisions required. Imagine we encounter the equation log base 8 of 0.125 equals what? This equation prompts us to determine the exponent to which we need to raise 8 to obtain 0.125. Since 0.125 is less than 1, we know the exponent must be negative. We find that 8 to the power of negative 1 equals 1/8, which is 0.125. Therefore, log base 8 of 0.125 equals negative 1. Negative logarithms prove particularly useful when dealing with quantities smaller than 1, such as probabilities, concentrations, or decay rates. They provide a convenient way to represent these small values on a logarithmic scale, facilitating comparisons and calculations.